Hello everyone. Today in lecture 17, we're going to finish up chapter 13, but first I would like to talk briefly about exam 2. We had an average of 71% and a median of 75%. As you can see, the scores are fairly evenly distributed, at least among the 10 and up range. 71% is actually really good. As you know, the average score on exam 1 was anomalously high, so it's nice to see a normal good score from you guys, so I'm happy about that. I did post solutions on Canvas a week or so back. Let me know if you want your exam back. You can see here that I use the same rubric as I did in the first exam. And then in the bottom right, you can just see how the points were awarded for each question. So you can see question 2 and question 10C were definitely the hardest of the bunch. If you have any questions about the exam, please let me know. I don't intend on going over the exam in video form, but if you have any questions, please just send me an email, and I'd be happy to go over it with you. In any case, let's move on to chapter 13. In lecture 16, we started talking about oscillations, springs, pendulums. Today we're going to talk about waves, and we're going to see how these things are related. So generally speaking, a wave is exactly what you think of when you think of a wave, like a water wave or waving your hand back and forth. To be a little more technical, though, in physics we say that mechanical waves are an oscillation, so a back and forth motion in a medium that transfers energy but not mass. The definition of medium is also fairly vague. Essentially, it just means anything that can move back and forth and allow a wave to travel through it in this sense. And I do want to point out that there are waves that do not require a medium. Electromagnetic waves in particular are something that we will talk about later in the semester. But for mechanical waves, we require 3 things. The first one is a source of disturbance. So if you look at the picture on the bottom, the source of the disturbance would be the hand that's moving the rope up and down. 2 is the medium that can be disturbed, so we require something that a wave can actually travel through. And then 3, we need some mechanism through which adjacent portions of the medium can influence each other. For this picture, these are just the bonds that hold the atoms of the rope together. If the left half of the rope couldn't communicate with the right half, then when the wave got to the middle point, there would be no way for the wave to transfer from the left to the right half. So 3 is sort of just a technical requirement. I would guess that most of the waves you're familiar with are of the transverse nature, as in the top picture. You wiggle the rope up and down, the rope makes a shape in the up and down direction, but the motion of the wave is to the right. There's another kind of wave called longitudinal waves, where the actual back and forth motion is to the left and to the right, and the motion of the wave is also to the right. If that's hard for you to visualize, I have an example and a few slides that should help you out. And the second bullet point here is important, so I want to go over it. It's kind of the main point of a wave. So notice that for both waves, the actual medium does very little of the moving, and it's actually the shape that has most of the motion. So imagine you have a ribbon tied to the rope, say right there. As the wave is approaching the ribbon doesn't move at all. When the wave hits the ribbon will start to move up, and then it'll get to the top, and then the ribbon will move back down. But the ribbon doesn't actually move left or right at all, so in fact it's more like that. The ribbon just moves up and then back down a little bit, but it doesn't move left and right. This big shape that's formed, This actually does most of the moving. It'll travel all the way down until it hits the end of the rope. And you'll see the same thing happens for a longitudinal wave in a few slides. So what's actually happening here is that the mass of the medium itself, the ribbon for example, is not being transferred, but energy is being transferred via this pulse all the way down the rope. For a longitudinal wave, it's similar. These little black dots mark regions that would just move back and forth a little bit, and then this scrunched up region would represent the wave that's traveling all the way down the slinky. Here's a quick question just to get you thinking. What type of waves do you see on the surface of the ocean? Unpause after you've thought about it. The answer may seem like it's obvious, so you start with a flat surface of water, then you have a bump that forms and it just travels across the surface of the water. So it looks like it's clearly a transverse wave. But actually, the answer is C here, and the reason for that we'll see on the next slide. If you were to go down to the beach and watch a seagull sitting on the surface of the water, you would see motion very similar to what's shown in the pictures on the right. The seagull starts at the bottom, and then the seagull will make a left motion. That motion will continue upward and then to the right, and eventually the seagull is going to go all the way back down to where it started. So the up and down portion of this motion, going from the bottom, say, to the top, this represents the transverse nature of the ocean wave. But the seagull also has a left and right motion, and that's because water waves, or waves on the surface of the ocean, are also longitudinal waves. You can see this in action in the GIF at the bottom. You have a wave that's traveling to the right along the surface, and then you have this little yellow dot that's spinning around. This would represent the seagull sitting on the surface of the water. And if you follow the little dot around, you can see that it's making this circular motion. That's because the combined effect of the transverse and the longitudinal waves of the water is this circular motion. So basically the dots go up and down and the dots go left and right, but if you follow any individual dot around, you'll see that none of them actually travel that far. The shape of the wave, though, travels all the way across the surface. And actually, if you look down below, you can see that the lower dots barely move at all. So for water waves, it's actually the surface that does most of the wave motion. I guess you could say this is important for a few reasons. Surfers literally ride the transverse waves, right? This is how they propel themselves through the water. And longitudinal waves are also important, in particular for animals under the surface of the water. They use this for echolocation. And this is actually a general feature of sound wave. Sound is a longitudinal wave that travels through mediums such as air. The GIF at the bottom is a good example of a sound wave, but it's also just a longitudinal wave in general. So let's look at the GIF a little more closely. If you follow the motion of any individual part of the medium, for instance the highlighted red particles, you'll see that they move back and forth just a little bit, but none of them actually transfer very far in the medium. If you follow the black arrow at the bottom, you'll see that the black arrow represents the wave, and the waves travel all the way down the medium. So just like transverse waves, you have a part that moves back and forth just a little bit, and that's the actual medium itself. And then you have a part that transfers all the way across the medium, and that is what we call the actual wave. Now with transverse waves, you have a few parts that you can point to. So the high part here, we would call this the peak, and then the low part, we call that the valley. And longitudinal waves also have two parts that we can point out. There's a compressed region that we would sort of identify with the peak, and that's what's actually pointed to by the black arrow here. You also have a region between two compressed regions that I'm pointing to here that is sort of more spaced out than the compressed region. We would call this the rarefied region, or rarefaction. And you can think of the rarefaction as the valley of the wave. To show you how this represents a sound wave, imagine somebody on the left side here, and they are speaking. They are the source that's causing air molecules to bunch up right in front of their mouth. Then those bunched up air molecules travel down the medium as the wave is traveling, and it's also causing the rarefied regions between the compressed regions. And then one more thing before I move on, I just want to point out that sometimes the peak of the wave is also called the wave crest, and sometimes the valley of the wave is called the wave trough. This slide basically summarizes part of what I was saying on the previous slide. You have the regions where it's more bunched up, the compression regions. In these regions, the particles are bunched up, so there's a higher pressure. So if you were to graph that, as in the bottom right picture, these regions would have a high pressure. In the more spread out, or the rarefied regions, there is less pressure. So if you were to plot this on the graph, it would correspond to a region of low pressure. So then the compression regions are sort of like the peaks of the wave, and the rarefied regions are kind of like the troughs of the wave. This slide just has some definitions that we will quickly go over. The amplitude is the maximum height of the wave. So to be clear, if you're looking at the wave in a vertical direction, then the amplitude is the distance from the center of the wave to the top of the wave. And similarly, you could measure it as the center to the bottom of the wave. So for us, unless it's very obvious, we're going to assume that the height of the crests and the troughs are always equal. Next is the wavelength. So if you start at, say, the peak of one of the waves, and you trace out the shape of that wave until you get to the next peak, then you have traced out one wavelength. So the distance from peak to peak would give you the wavelength of the wave. And this doesn't only work for peak to peak. You can also do trough to trough, for example. So if you start at the bottom of one of the waves, and then you go up and you go back down to the next bottom, this also gives you the wavelength of the wave. And for most of our purposes, these distances will always be equal. For the period, you have to imagine the wave traveling to the right, for instance. Then the period would be the time that it takes for the shape of the wave to travel the distance of one wavelength. We define the frequency as to be 1 over the period, and this gives you the number of waves that actually pass by a point per second. And then the wave speed is just how fast the shape of the wave is traveling. So if you want to say that velocity is equal to distance over time, then for a wave, the speed of the wave would be the distance it travels divided by the time that it takes to travel that distance. So lambda divided by capital T. And then you can rewrite that as lambda times f using the definition of frequency. Here's a quick example related to those definitions. So read through and unpause when you're ready. So the amplitude is just the height of the wave from the middle to the top. In this case, that is the same as delta y, so it will be 15 centimeters. The wavelength is going to be the peak-to-peak distance. In this case, it is the same as delta x, so it will be 40 centimeters. The period is the next easiest. We just say that period is equal to 1 over the frequency. So in this case, it is 1/8 hertz. The 1/8 part we can just write as 0.125. And then the 1/hertz, if you remember correctly, a hertz is 1/seconds. So the period is going to be 0.125 seconds. You have 1/1/seconds just gives you seconds. And then finally the wave speed. The wave speed we can get as lambda times f using the explanation I gave on the previous slide. So you have 40 centimeters times 8 hertz, which gives 320 centimeters per second. So now I want to connect this wave motion to what we learned about in the previous lecture. So imagine you have a rope and you tie a ribbon to the rope, then you wiggle the rope up and down, and you just watch the motion of the ribbon. It'll follow the same motion that these black dots are following in the wave shown to the right. The little black dot, as it's going upward, it has to slow down when it gets to the top so that it can turn around and start going downward. Then it picks up speed, it passes over the center. As it gets to the bottom, it has to slow down because it's about to turn around and go upward. And hopefully this sounds familiar because it's the same description I gave for simple harmonic oscillation. Now, technically there's a few more requirements for it to actually be SHO, but I've superimposed a spring onto this wave to demonstrate that they are the same type of motion. So if you follow the little black dot, you'll see that it should match up pretty closely with the motion of the weight on the spring. Now it's not perfect because it was hard to get the simulation of the spring to match perfectly with some random GIF I found on the internet, but hopefully it links the two ideas in your mind. Now, when I defined period of oscillation in the last lecture, here it would correspond to the time that it takes for the ribbon to make one complete cycle, so to go all the way from the top to the bottom and then back to the top. For waves, this corresponds to the period of the wave. It's the time that it takes for the wave to travel one complete wavelength. And then the last two bullet points here are things that I have already talked about, so let's move on. In this question, you have 3 different waves shown on the graph, and you have to imagine all of the waves are traveling to the right. The question says that they all have the same frequency, and it asks which one has the largest speed. So here you kind of have to piece together those definitions that I gave a few slides ago. So think about it and unpause when you're ready. The wavelength v is equal to lambda times f. Since all 3 of the waves have the same frequency, the faster waves will be the waves that have a larger lambda, or a larger wavelength. So we have to determine the wavelength for each of the waves. That means we have to trace out one repeating pattern for each wave. So with wave A, if we start at the origin, we have to go up, down, and then back up again. Right, we have to trace out the full repeating pattern, so we need to get one peak in there and one valley in there. That tells us that the wavelength for the red wave, for wave A, is 2 meters. If we do this for wave B, start at the origin, we go up, down, and then back up to where we started. We get a wavelength of 4 meters. And then if we do this finally for wave C, we start at the origin, go up, down, and back up again. We get also a wavelength of 4 meters. Okay, so the wavelengths the waves with the longest wavelengths would be B and C, And these are the waves that have the largest speed. So the answer here is E. And wave A with a wavelength of 2 meters would then be moving a little bit slower. The equation for wave speed that we've seen so far relates the velocity of the wave to the wavelength and the frequency, and this is true for any wave. But for mechanical waves in particular, the wave speed is actually determined by the medium. So what I mean by that is, if you have one particular type of rope, every wave that travels down that rope will have the same wave speed. And then if you have maybe a thinner string, then every wave that travels down the string will have the same wave speed, but the speeds between the rope and the string will be different. You can determine the speed of a wave on any given string using the formula in the middle. You have that the wave speed is equal to the square root of the tension in the string divided by what we call the linear mass density of the rope or of the string. So tau is the symbol we're using now for tension, and mu is equal to the mass of the string divided by the length of the string. So this is sort of like a one-dimensional version of density. Now I do want to point out that this wave speed is the speed of the shape, the actual wave pulse. It's not the speed of the ribbon, the thing that goes up and down. And then all waves that are moving on this particular string that has this value of tau and this value of mu will have the same speed. So I'm just giving you this formula. If you want an actual proof of it, you need calculus and geometry. However, you can verify it using dimensional analysis. So verify it using dimensional analysis and unpause when you're ready. So this is a little tricky maybe because you have to rely on knowledge that you have gained in the past, and I know you guys hate doing that, but here goes. On the left side you have velocity, and velocity has dimensions of length per time. So you could say, for example, meters per second. On the right side, you have tau. Tau is tension, and tension's a force. So tau has dimensions of force, and for that we can use newtons. So let's say newtons. And a newton is equal to a kilogram times a meter per second squared. And then finally mu. Mu is mass per length, so it has dimensions of mass divided by dimensions of length. So for that we can use kilograms divided by meters. Okay, and now you need to piece it all together. For the right side, the dimensions of the square root of tau over mu would be the square root of kilograms times meters per second squared, and then all of that divided by kilograms per meter. Now we want to simplify the inside a little bit. The kilograms are going to cancel with the kilograms. The 1 over meters in the denominator is going to flip over so that we get meters in the numerator, and that leaves us with actually 2 meters in the numerator. So you multiply those together, you get m squared, and then you still have s squared in the denominator. So when you take the square root of m squared per s squared, you get meters per second. So the left side has units of meters per second, and the right side has units of meters per second, and the equation is verified using dimensional analysis. Now that we have two equations that are related to wave speed, we can sort of combine these equations to relate all the variables together, and that's what we do on this slide. So I start with the equation from the previous slide. I actually just start by squaring that equation, and then I rearrange some things to get to the middle equation. Then in the middle equation, I take for v, I plug in lambda f. So I get tau is equal to lambda squared times the frequency squared times mu. Now, if you play with this a little bit, you can actually find this equation shown at the bottom. And this equation you'll actually use in lab today. You're going to use a slightly different form of it. Instead of tau, the lab manual uses the symbol F for that tension force. And instead of mu, the lab manual uses the symbol rho for the linear mass density of the string. This question is going to be a little bit confusing without me being present to answer the questions that you're going to come up with, so let's just go over it. It says that a wave pulse on a string travels with a certain speed. You double the length of the string and you double the tension in the string. And then it asks, what is the speed of the wave pulse now? So we'll start with the equation V is equal to the square root of tau over mu. For mu, I'm going to plug in mass per length. Now, if I start with a string that's, say, I don't know, 1 meter long, and I double that, I have now a string that is 2 meters long. So I've doubled the length, but I've also doubled the mass of the string. So the mass is going to go to 2 times the original mass, and the length is going to go to 2 times the original length. And then we also double the tension, so tau goes to 2 times tau. And now I want to see what happens when I change these variables. So I start with an initial speed of tau 0 over m0 over L0, all square root. And then those things get doubled, so I have the square root of 2 times tau 0 divided by 2m0 over 2L0. In the denominator, the 2's are going to cancel out, and that leaves me with 1, 2 in the numerator, which I will factor out of the square root. I'm going to have the square root of 2 times the square root of tau 0 over m0 over L0. Okay, so I have the square root of 2 times the thing that I started with. So the speed of the wave on the pulse, the speed of the wave pulse on the string increases by a factor of square root of 2. So the answer here is B. Basically what I'm saying in this problem is that even though you're doubling the length of the string, this changes the length, but it doesn't change the density of the string. So you have to also change the mass of the string. Now we're going to talk about how 2 waves can affect each other. The short of it is that 2 waves can pass through each other without affecting the individual waves, but as they're passing over each other, they do combine to form a new wave. Let me start by showing you a clip from YouTube of this happening in real life. So the clip starts by dropping a rock into a pond. From the impact point, you can see these waves start to spread out. And then also you have these large drops of water that end up hitting the water and creating new waves. So in the bottom right corner, this is a good example. You had an impact here and waves start to spread out from this region. As the smaller circles reach the bigger circles, you can see that they interact with each other, but eventually they pass through each other. And at the end, neither wave was affected, but while they were passing over each other, they did affect each other. In physics, the way that the 2 waves combine is called superposition, and we can see it more clearly on the slides back here. So the superposition principle says that when 2 or more waves overlap, the resultant wave is found by adding together the displacements of the individual waves point by point. And maybe we can make more sense of it by looking at the simulation in the bottom right, so let me explain. The blue wave is traveling to the left, and the green wave is a wave that's traveling to the right. The red wave is a superposition of the green and the blue waves. To find the height of the red wave, we use this formula here. It says that the height of the red wave is equal to the height of the blue wave plus the height of the green wave at any particular point. Let's look at that a little more closely by pausing the video right there. That's good. Okay, so at this point, minus 2.5, the blue wave has a height of about, I would say, 0.9, and the green wave also has a height of 0.9. So when you add those two heights together, you get a larger height, which in this case is a little more than 1.8. You can also do this for the valleys. Here you have the green and the blue valleys at just a little bit more than minus 0.9. When you add those together, you get just a little bit more than minus 1.8. And let's do this at one more time when the waves are sort of anti-overlapping. Say right there. No, let's try again. Say right there. That's perfect. Okay, so now if I look at x is equal to 0, I have a blue wave that has a height of 1 on the y-axis, and the green wave has a height of minus 1 on the y-axis. So if I take the blue value of 1 and I subtract the green value of 1, I get a red value of 0. So the resultant wave at the origin here has a height of 0. And for this particular anti-overlapping pattern, you can actually do this at any point, and you'll find that the red wave always has a height of 0. So to summarize, for each point on the x-axis, you add together the height of the waves, and that gives you the height of the resulting or the resultant wave. We saw two types of wave interference on the previous slide. First, when the two waves combined to create a larger wave, we saw constructive interference. That is when the new wave has a larger displacement than the individual waves. In this case, we say that the waves are in phase with each other. And then we also saw destructive interference. That was when the two waves combined to have a smaller displacement than the individual waves. In this case, we would say that the waves are 180 degrees out of phase with each other. The pictures at the bottom basically show what I was demonstrating in the simulation, so let's move to the next slide. This slide shows a closer view of the two types of interference from the previous slide. Let's start with the left column with constructive interference. Let's start by looking at the triangular wave. The triangular wave is centered at x is equal to 1 meter, and it's moving to the right at 1 meter per second. So let's follow this wave and ignore the rectangular wave for now. After 1 second, this wave has moved over to the right by 1 meter, so it's centered at x is equal to 2. After 2 seconds, it moves over another meter. After 3 seconds, it moves over another meter, and after 4 seconds, it moves over 1 more meter. So now let's look at the rectangular wave while ignoring the triangular wave. The left end of the rectangular wave is at x is equal to 4 meters, and the rectangular wave is moving to the left at 1 meter per second. So after 1 second, it has moved to the left by 1 meter. After 2 seconds, it has moved to the left by 2 meters. After 3 seconds, it has moved to the left by 3 meters. And after 4 seconds, it has moved to the left by 4 meters. Now in pictures 1, 2, and 5, the waves are not touching each other at all, so they're just not affecting each other in any way. In the third and the fourth picture, the waves are overlapping. So to figure out the effect, or what the resultant wave would look like, we have to add together the amplitudes of the waves point by point. So let's start in the third picture at the point x is equal to 2. The height of the red wave here is 0, and the height of the green wave is, let's say, 1. So you're adding together 1 centimeter with 0 centimeters, and the resulting wave will have a height of 1 centimeter. If you go to the point 2.5, then the red wave has a height of 0.5, the green wave has a height of 1, so 1 plus 0.5 gives you a height of 1.5. At x is equal to 3, both the red and the green waves have a height of 1. So when you add those together, you get 1 plus 1 is 2. And the resultant wave has a height of 2 centimeters. So if you do this for each point, you get a triangle on top of the rectangle. And then between 4 and 5, the red wave doesn't exist at all. So the green wave just looks like the green wave. Now it looks like I just took the red wave and I put it on top of the green wave, but let me caution you against doing that and say there was a reason why I added the waves together point by point. And this is maybe more clear in the fourth picture down here. So from x is equal to 1 up until x is equal to 3, the green wave is the only wave, so the resultant wave will look just like the green wave. At x is equal to 3, we take 1 for the green, and we take 0 for the height of the red wave. That gives us a height of 0. At x is equal to 3.5, we have a height of 1 for the green wave and 0.5 for the red wave, so we have a total height of 1.5. At 4, the green wave and the red wave both have a height of 1, so we add them together and we get 2. X is equal to 2. If we go a little bit past 4, let's say 4.1, then the red wave has a height of just below 1, so we'll say 0.9, and the green wave has a height of actually 0. So you're doing 0.9 plus 0, which gives you actually a height right here of 0.9. Or I guess another way to think of it is that after x is equal to 4, the green wave doesn't exist. So the only thing we have is the red wave, which means that the resultant wave will look exactly like the red wave. Okay, so then the total wave is going to start with the green wave, and then you have a combination of red and green, and then you have just the red wave, and then you have nothing. So it doesn't make as much sense, I think, to just put the triangle on top of the rectangle if they're only halfway overlapping. But we can also see why this is a problem by looking at the destructive interference in the right column. So let's again start by following each of the individual waves. We start at the top at t is equal to 0 seconds with a triangular wave pointing up at x is equal to 2 meters. The wave is traveling to the right at 1 meter per second. So after 1 second, the wave has moved to the right by 1 meter. If we move forward another half a second, the wave will have moved half a meter to the right. After another half second, the wave will have moved another half meter to the right. And then after 1 more second, the wave will have traveled 1 more meter to the right. The same thing is happening with the downward pointing wave. It starts off at x is equal to 5. It moves over to x is equal to 4. Then x is equal to 3.5. X is equal to 3. And x is equal to 2. So in the first and the fifth, the waves aren't interfering at all, and it just looks like 2 individual waves. But in the second, third, and fourth picture, they are. To figure out how they're interfering, we add together the amplitudes at each point. So if we start in the second picture, you're adding 0 to 1, and that gives you a resulting wave of height 1. If you move over a little bit, you're adding minus 0.5 to 0.5. That gives you a resulting height of 0. And then if you move over to x is equal to 4, you're adding -1 to 0, so it gives you a resulting height of -1. So then the resulting wave will start off as nothing. It will then look like the red wave. Then the red and the green combine to give you this sharper diagonal. And then after x is equal to 4, red is gone, so it just looks like green and then nothing. Okay, so in the third picture, the waves are perfectly anti-overlapping, so if you add together the heights at any two x values, they will actually just perfectly cancel each other out, and the resulting wave will look completely flat. In the fourth picture, you have the same thing that's happening in the second picture, but sort of in reverse. So you have that sharper incline in the center where the two waves are actually overlapping with each other. Okay, now you do it. You start in the top right. You have a rectangular wave and a quadrilateral wave. They are both moving at each other at 1 meter per second. And the picture in the top right is shown at t is equal to 0 seconds. All the pictures in A, B, C, and D happen at t is equal to 2 seconds. So what will the string look like at t is equal to 2 seconds? I really want you to try this one, so pause it, take your time trying to figure it out, and unpause it when you are ready. Okay, so let's start by looking at what's happening with the individual waves. At t is equal to 0 seconds, the rectangular wave is as shown. After 1 second, the wave moves 1 meter to the right, so it will look like this. And then after 2 seconds, the rectangular wave will move 2 meters to the right, and it will look like these squiggly lines right here. Okay, now let's do it with the trapezoidal wave. At t is equal to 0, the trapezoid is as shown. After 1 second, the wave moves 1 meter to the left, so it will look like the dashed lines here. And then after 2 seconds, the wave will have moved 2 meters to the left, so it will look like the squiggly lines shown here. Okay, so just to be clear, let me clean this up a little bit. Now at t is equal to 0, the waves are shown in black. At t is equal to 2, the rectangular wave will look like that. And at t is equal to 2, the trapezoidal wave will look like this. Now we have to add them together point by point to find out what's happening with the resultant wave. So at x is equal to 3, you have only the green wave, which means the resultant wave will look just like the green wave. At 3.5, again, you have just the green wave. When you get to x is equal to 4, you have the waves start to overlap. So you have the purple wave is going to look like the green wave all the way up until x is equal to 4. Then at x is equal to 4, the green wave has a height of -1, and the red wave has a height of 1. So you do -1 plus 1 gives you 0, and the resultant wave will have a height of 0. When you go from 4 to 5, you're going to be adding -1 to 1, so they're going to cancel each other out in this entire region. At 5, you have -1 plus 1, so it's still 0. When you go a little bit past 5, this is when things start to change. You have a height of -0.9, let's say, and you have a height of 1. So when you add those together, you have just above 1, right? So just to be clear, I'm doing 1 minus 0.9. Okay, so then the height of the resultant wave will be just above 1, right here. When you go to 5.5, you have a height of 1 and you have a height of minus 0.5. When you add those together, you get a height of 0.5. And then if you keep doing this, you'll get this triangle shown here. Okay, so let me draw the resultant wave in, I don't know, how about light blue. It starts off on the x-axis, then it looks like the green wave, then they start to overlap, then they cancel each other out, and then they overlap again up here, and then there's no waves at all. Okay, so the picture that I just drew matches up with picture A, so the answer here is A. Now, this can be very confusing, I understand that. So try to work through the example again, work through the previous slide again, and if you have any questions, please let me know. Otherwise, we are going to move on to the next slide. Here we talk about what happens when a wave hits a wall. So let's say you start with a string that's attached to a wall, and you send a wave down the string. As the wave approaches the string, it just has the normal wave-like shape. When the string starts to hit the wall, imagine what's happening to the wall, or let's say that you're holding one end of the string. When the wave gets to you, that wave is going to cause your hand to go up, right? In the case of the wall, when the string tries to pull the wall upward, the wall exerts an equal but opposite downward force on the string. This downward force causes the string to actually go down as it moves backward. So then after the wave hits the wall that it is attached to, that the string is attached to, the resultant wave is inverted as it reflects off of that wall. The moral of the story is the second bullet point here. When a string is fixed on one end to a wall, then the reflected wave will be inverted. So if it starts out up, it will flip over so that it's down on the way back. If the string is not fixed on the right end, then this doesn't happen, because when the wave gets to the, in this case, the pole, there is no downward force by that pole. The wave pulls the ring upward, and then the wave pulls the ring back downward, and the wave just reflects off, just like it looked when it was coming in. So the moral of the story here is the first bullet point. If the end of the string is free to move up and down, so it's not fixed, then the reflected wave will be upright. If it starts upright, then the reflected wave will be upright. Now, I can show you this happening in real time with the simulation from the link that's shown on the slide here. But that link is mostly for you to play around with. Let's take a look at it in any case. Here I have a string that is fixed on the right end, held in the vice grip there. When I send a wave pulse down the string, the wave is upright. When it hits the wall, it reflects off the wall and it becomes inverted as it reflects off that wall. Now, if I were to have the right end be not fixed, loose, then as I send the pulse down the string, it is upright. As it reflects off the end point, it remains upright while it's reflected. So the main two things that I want you to remember from these slides are the bullet points that I highlighted. When a string is fixed on one end, the reflected wave is inverted. If the end is free to move up and down, then the reflected wave is upright. Now, these last few slides are not necessarily important for, say, upcoming exams, but they're still interesting and relevant to real life, so I still want to talk about it just a little bit. So in real systems, you have friction, and friction, generally speaking, always reduces the mechanical energy over time, right? Frictional forces always result in a loss of total energy for a system. We know that the energy is lost by the system, but generally speaking, friction will cause a surface to heat up, so energy is still conserved, but the actual system itself loses that energy. And this happens in systems that are oscillating as well. So basically, if you have a spring and the spring is oscillating back and forth, eventually that spring is going to come to a rest because friction is sucking away the energy for that spring. Another example is pendulums. So you can think of maybe somebody swinging back and forth. So you have somebody on a swing, you push them, they move forward, they come back, forward, back, and eventually they come to rest at the bottom of the swing. This is again because friction is eating the total energy of that swing system until the swinging motion has stopped. So friction is sucking up the total energy of the system, and of course, as the motion begins to stop, the amplitude of oscillation is decreasing. And if you remember back to last lecture, these two things are actually related via this formula. The energy is proportional to the square of the amplitude. So as friction reduces E, it's also reducing the amplitude of oscillation. And generally this happens quite quickly in real life. In the picture on the right, we can see that you start with a large oscillation, and friction is reducing the amplitude of that oscillation until it's essentially zero and motion has stopped. Sometimes we think of friction as a nuisance. So in a car engine, for instance, the parts rub against each other. This causes the parts to heat up, and that heat can damage the engine over time. In a car engine, they run oil through different parts of the engine to reduce the friction between the different parts of the engine. Another example is in a computer. Because of the electricity that's running through the circuits, you have the resistance in the wire, which is essentially friction, and this causes the wire in the different parts of the computer to heat up. And oftentimes they'll create rather elaborate systems to cool off the computer and reduce the damage that's caused to the computer over time. However, we can also take advantage of friction. For instance, the shocks in your car are sort of just elaborate springs. So when you go over a bump, the car goes up and down, and shock absorbers work by dampening that unwanted spring motion. In a shock absorber, you have two tubes. You have this outer tube and the inner tube. Between the two tubes, you have oil or some other type of viscous fluid, and then you have a piston at the bottom with little holes in it. Now when the car goes over a bump, the outer tube and the inner tube rub against each other, and the fluid is forced through the holes at the bottom in the piston. The viscosity of the fluid sort of in a way acts as friction for this system, and that friction eats away at the amplitude of the up and down oscillation, so that your car, instead of bouncing up and down a lot, it eventually comes to a rest after you go over a bump. Now there are three different types of damped oscillations, and the three different types depend on the strength of the frictional force. So when the frictional force is weak, we call it underdamping. This is case A here. An example of underdamping, you can think of somebody on a swing. So you have somebody sitting on a swing, and you push them, and they move in one direction, then they move back, forward, backwards, until they slowly come to a rest. The reason that this is underdamping is because the frictional force, the friction is coming from, I suppose, a little bit from air resistance, and then also a little bit from this joint that's holding the swing up. So you have a weak frictional force that's slowly causing the person to come to a rest. This is shown in the graph on the right as this slowly decreasing oscillation. The second type of damped oscillation is called overdamping, and this happens when the frictional force is very strong. The frictional force in the overdamping case is actually so strong that it prevents oscillations altogether. This is shown as the black line in the graph. So you start with what looks like it's going to be an oscillation, but there's so much friction that the object is not even allowed to cross over the equilibrium point at the center. So I guess an example of overdamping, you could also think of a person swinging. So if that's A, this would be C. You have a person, you push them forward so they're sitting on the swing, but before they swing back, you actually grab them. And then you slowly allow them to go back to the center. But you don't actually allow them to swing. So I guess when you're stopping someone from swinging, this is sort of like overdamping. And the third case is called critical damping. This is, it's very similar to overdamping, but it's when that frictional force is sort of just right. And this is shown by the red line in the figure. You can see it looks very similar to the black line, but the red line quickly approaches that equilibrium position, and it is not allowed to cross over the center. Overdamping and critical damping, they look very similar to one another, and in practice it would be hard to tell which is which. Really it comes down to the math involved, and this is math that I'm not going to get into, but you can just know that overdamping and critical damping differ because of the math that's involved with oscillations. So that's all I have for you today, and that ends chapter 13. As always, if you have any questions, please let me know, and have a good day.